Hello, my name is Alejandro and I'm a postdoc at the Tianjin Center. Today I'm going to talk about the effect of a constant velocity of the source on gravitational waves. Let's first start with the motivation. Traditionally, gravitational wave sources have been described in a quite idealistic manner, where we have a source that evolves isolated, emit gravitational waves, and we detect them far away here on Earth. However, more recent studies have shown that gravitational waves actually evolve in very dense systems. This is easy to understand because we need dense systems in order to get two black holes, two neutron stars, whatever, close enough so that they can form a binary that is emitting gravitational waves. And in such dense systems, there are a lot of things lurking around. For example, gas, other stars, other compact objects, the supermassive black hole in the center of a galaxy, or the galaxy itself, the host system, can be embedded in other systems and therefore having an interaction. Understanding these systems and their interactions is important for us for two reasons. First, we still want to have a very accurate description of the gravitational waves emitted and of the evolution of the system. Therefore, we require to understand all these interactions and include them in the evolution so that we still can perform this very exact somehow idealistic description of the source in order to really get the information we want to have about GR, about the evolution of the system itself, and so on. The second reason why we want to understand these interactions is because we also want to use gravitational waves to perform astrophysics or astronomy. It means to really observe the system and extract information about the system from the gravitational waves. For that, obviously, we also need to understand the interactions. One thing that many of these interactions, if not all, have in common is that they induce a motion of the center of mass of the source. Therefore, I think velocity is a very interesting characteristic or parameter of a gravitational wave source. And two kinds of velocity here stand out particularly. One is the peculiar velocity of galaxies. As I mentioned before, galaxies also can be in systems, in galaxy clusters, and these are very huge objects containing dozens or hundreds of galaxies, and therefore they are moving with velocities that have been measured with light and are in an average of 1000 kilometers per second, but can even go above 2000 kilometers per second. Obviously, the systems in the galaxies are also going to move with these velocities, and therefore they are going to appear for us as a distant observer moving with these velocities. This kind of motion is very interesting because on the first hand, the velocities are quite considerable. 1000 to 2000 is definitely far away from being at rest. And second, because this is going to affect many, if not all, sources, because we believe most of the gravitational wave sources form in galaxies. The second kind of motion that is important for us is triples. As I said, we need dense systems so that we get a binary, but if you already have a binary, you are not far away from also getting a triple, at least for some time. And if the binary, which is emitting gravitational waves, is in a triple, its center of mass is going to feel some orbital motion. This orbital motion can start just from tens, but up to hundreds of kilometers per second. And it also can go to thousands or highly relativistic velocities, depending on how far it is from the triple. In particular, when the third body is the supermassive black hole in the center of the galaxy, velocities of almost 10 or 20% the speed of light can be reached. So this is also very interesting because it can apply to many sources, at least for some time, and because it can be very extreme, so that we really need to understand it in order to include such a possibly very important effect. Okay, we know now that we want to understand the effect of velocity, and fortunately this can be done in a quite simple manner, dividing it into the different effects which velocity can cause on a gravitational wave. The first one is the Doppler-shift, which basically makes that the gravitational waves emitted along the velocity or parallel with the velocity appear blue shifted, and those anti-parallel appear red shifted, while those perpendicular almost do not change. This basically leads to the fact that the frequency that we are seeing is changed by some factor depending on the velocity and the direction. On top of that, the Doppler shift also causes a change of the perceived luminosity and therefore of the luminosity distance that we are seeing by dividing by the same factor. The Doppler shift is also that what most people take into account, but it's not the only effect. there are also the aberration and polarization rotation. First, the aberration, this basically makes that the gravitational wave rays that are being emitted tend to point more towards the direction of the velocity. This causes a change of the directions of the rays relative to their system, also depending on the velocity perpendicular to the line of sight, which is going to be important in an explanation that I will give you a bit later. The second part of the aberration, maybe more important, is that the solid angular change. So the amount of energy that is emitted in a solid angle is changed by the velocity, so that the intensity of the field is also changed. Last but not least, there is the polarization rotation. Gravitational waves have a preferred direction, for example, the direction in which the plus polarization is the strongest, and the polarization rotation causes that these directions are rotated in the plane. What does this mean for the detection of the gravitational waves? For that, we can look on the complex amplitude, so the combination of the plus and cross polarization seen by a distant observer in terms of the plus and cross polarization in the source's rest frame. As I said, there is the polarization rotation. The polarization rotation basically causes a mixing of the plus and cross polarization. So the plus polarization, for example, in the observer frame is a combination of the plus and cross polarization in the source frame. Second, there is the change of the perceived amplitude of the source. Here for the velocity, it's very interesting that if it would be only the Doppler-shift, we would have here a factor of d, but due to the aberration, which enters with a factor of 1 divided d squared, it ends up being divided 1 by d, so that, for example, red-shifted sources appear closer and blue-shifted sources appear further away. This is in contrast to the cosmological expansion, where, for example, red-shifted sources appear further away and blue-shifted sources appear closer. The last effect is the Doppler-shift on the frequency, and here it is important to say that this is a change of the fundamental frequency. However, gravitational waves usually have several modes, and each mode has a frequency which is a multiple of the fundamental frequency. So by changing the fundamental frequency due to a constant factor, this does not directly translate in a change of the measured frequency by also the same constant factor, due to the fact that the different modes enter with a different proportion, and this proportion can also change in time. Okay, taking into account these effects, we decided to look on one example. The example we consider is a standard extreme mass ratio in spiral. By standard, I mean a supermassive black hole of 10 to the 6 solar masses, a small black hole of 10 solar masses circling in a quasi-circular orbit 1 year before plunge. And we set this EMRI to be at a distance of 0.1 gigaparsec. This is about the distance of the coma cluster. For such an EMRI, we would have a signal-to-noise ratio of about 200, which is quite high, but nothing extraordinary high, let's say. And for that, Chang Ye, a student here at the Tianjin Center, has helped me to look on how, for such a source, how the accuracy of the measurement of different parameters would be affected using a Fisher matrix analysis. There we consider a source being at rest relative to the observer, moving with the velocity of 2000, corresponding to the higher velocities of the galaxy cluster or in galaxy cluster, and 3000, which would be basically the sum of different velocities coming together. Here, if we look on the detection of the velocity, we find that the magnitude is actually going to be measured with a very high accuracy of 2 kilometers per second. Of course, this is a Fisher matrix analysis and it may be idealistic, but even if it would be a factor 10 worse, it still would be 20 kilometers per second, which is very good, better than light, or at least in a similar accuracy than what we can achieve with light. Second, we also can look on how the directions can be measured. Here the accuracy is not as good as for the magnitude. It's about 1 radiant. However, as I mentioned, this is also the dependence of the velocity that is perpendicular to the line of sight. So we could get information about not only the velocity parallel to the line of sight, but also perpendicular, which is something we cannot achieve with light, and therefore will be completely new information. And then last, we also can look into the, for example, intrinsic parameters, which in principle do not depend directly on the velocity. However, as we see, the detection accuracy for these parameters is going to be changed when a velocity is in there, or for example, there can be a dependence induced of these different parameters when there is a velocity. This is very important because even if you are not directly targeting the velocity, you want to have as accurate as possible information about your source. So you need to take into account that there is the velocity in order to really extract the correct information. Okay, that's all. Thank you very much for your attention. Bye bye.